Welcome back to The Explainer. Now, if you follow the tech space at all, you know there is this massive, almost invisible push happening right now to make AI computationally cheaper to run. Behind the scenes, engineers are just constantly tweaking and shrinking models so they use less memory, less energy, and fewer servers. It's a process called quantization, and honestly, it's kind of viewed as the holy grail of scaling up artificial intelligence. But today, we're looking at a totally fascinating new paper by Dr. Mohamed Radi that fundamentally challenges this purely technical approach.
Because we really have to ask ourselves, does aggressively cutting these computational costs actually save time and energy in the real world, or are we just, shifting the burden of that cost from the machine right back onto you, the user?
Dr. Ray actually captures this perfectly with the statement, the cheapest answer to generate is not necessarily the cheapest answer to use. And that quote right there, that is the core mystery of our explainer today. We're going to unpack exactly why optimizing for the machine sometimes creates massive, super frustrating inefficiencies for the human sitting at the keyboard.
Okay, let's dive into this. Part 1, the illusion of cheap AI.
Right now, the AI industry views efficiency almost entirely through a machine-centered lens. Actually, scratch that. For a lot of these companies, it's exclusively a machine-centered lens. Currently, success is measured by machine-side metrics, like how much energy does it take to generate a token, or how fast is the latency. But this totally ignores the real-world metric that actually matters to you and me, which is the total cost to reach a satisfactory outcome. A narrow technical view celebrates saving a tiny fraction of a cent on server energy, but it completely ignores the holistic, human-centric view of actually getting a usable, high-quality result.
Which brings us to Part 2, the hidden cost of errors.
To understand why this matters so much, we have to talk about what happens when things go wrong. When we talk about low numerical precision in AI, I know, it sounds super abstract, but you've absolutely felt it. It's that incredibly frustrating daily experience of an AI giving you a really fast but slightly flawed answer. Let's walk step by step through what actually happens in this rework loop. Step 1, you ask a question, and the model gives you an answer that is almost right, but it misses a key nuance. Step 2, you spend your own time writing a correction. Step 3, the model responds again, but confusingly, it carries forward a part of that original error. Step 4, frustrated, you have to completely reprompt or just hit regenerate. I mean, look at all that wasted human time and effort. The initial computational savings of that so-called cheap first pass are completely erased by this multi-turn repair sequence.
And the hard data backing this up is staggering. Recent research found that aggressive quantization, meaning dropping the precision of the model to save space, introduces up to a 32% accuracy degradation on complex mathematical reasoning tasks. For super simple tasks, low precision is fine. But for complex, multi-step logic, the errors literally snowball, forcing expert users to intervene heavily.
And it actually gets worse when you look at trust. In a recent user study, human evaluators rated these lower precision, quantized outputs lower, showing an 8.5% drop in trustworthiness and coherence compared to the full precision models. But here is the kicker, and this is wild. Automated AI benchmarks completely missed this drop. The AI grading itself thought everything was totally fine, but the humans could tell the answer felt subtly off.
So, how do we fix this? That's Part 3, shifting the optimization boundary.
The paper proposes something radical, shifting what we actually measure when we talk about AI efficiency. We have to move away from conventional precision optimization, which is the old way of looking only inside the machine. Instead, Dr. Ray proposes a pivot toward human-AI interaction-aware precision optimization. We are officially expanding the boundary to include the human.
And this brilliantly illustrates how it radically shifts our unit of analysis. We are no longer just looking at a model layer, a single token, or one inference pass in a vacuum. The true unit of analysis absolutely must be the entire human-AI interaction loop.
This allows us to build out a totally new, much more realistic mathematical equation. To get the true total interaction cost, you take the first-pass machine cost, which is what tech companies optimize for today, and you add the repair cost, the user's cognitive effort, and the cost of any downstream errors. This makes an abstract concept incredibly concrete. Think about it. If an AI writes a flawed legal summary quickly, the downstream error cost is astronomical. True efficiency simply has to factor in human fatigue and real-world mistakes.
Which leads us to the core solution in Part 4, precision as a dynamic resource.
So we need to start treating precision as a dynamic resource. Right now, precision is basically treated like a fixed hardware setting. But what if it were a fluid resource allocated dynamically based on the stakes of the specific task? Imagine two different users asking an AI to improve a paragraph. User A is just writing a casual email. They have a really high tolerance for approximation. They just want it to sound a bit smoother, instantly. For user A, a fast, low-precision answer is perfect. But user B, they're writing a complex scholarly manuscript. They have a very low tolerance for error, because fixing the AI's subtle, conceptual mistakes is going to take hours of expert correction. For user B, a slightly slower, high-precision answer is actually the cheapest and most efficient option.
So how does an AI actually know which user is which? Well, a system can use a diverse set of signals to dynamically route that computing power appropriately. At the prompt level, it detects if you're asking for a joke versus asking for code. At the conversation level, it detects if you've been having a deep, highly nuanced back and forth. At the model side, it detects its own mathematical uncertainty. And at the policy level, it respects minimum safety floors. The system dynamically reserves expensive, high precision for rigorous coding or legal analysis while saving energy on casual chit-chat.
And that brings us to the real-world application in Part 5, putting users in control. If precision is going to adapt to our interactions, how does that impact the actual interfaces we use every day? The paper issues a really critical warning here. Systems should never silently judge what quality of AI you deserve behind the scenes based on your user history. As the author notes, the ethical implementation is not hidden personalization, but governed personalization. It has to be totally transparent.
So the crucial point is that this control needs to be put directly into your hands. Imagine a simple slider letting users explicitly set their tolerance for approximation. You get to tell the AI exactly what you value for this specific session.
Or consider a setting specifically for rework avoidance. If you're working on something highly complex and you want to completely avoid that frustrating multi-turn repair sequence we talked about earlier, you can demand higher precision right up front.
And finally, imagine a setting for domain nuance. If you're an expert handling highly sensitive or dense topics, you can literally dial up the nuance you expect from the model, forcing it to use a higher precision compute path that won't just gloss over vital details.
Now, I do have to add a brief word of caution here. Even with all of these amazing user controls, the system absolutely still needs minimum quality floors. If someone asks a high-stakes medical or safety inquiry, the system cannot drop to a dangerously low precision just because the user's slider happens to be set to fast. There must be safety nets that prevent dangerous errors regardless of your personal settings.
Which brings us to our final thought. The next time you see a flashy headline about a massive new leap in AI efficiency or some ultra-fast new model, I want you to ask yourself this drop-the-mic question. Are they optimizing for the machine or are they optimizing for the human? True efficiency isn't just about saving server energy, it's about valuing your time, your effort, and your trust. Thanks for joining me on this explainer, and I really hope this leaves you rethinking your own daily interactions with these tools. See you next time.